So yeah, feel free to interrupt me at any time with questions. This is meant to be an educational experience, so yeah, if anything's unclear, if you have any questions, yeah, don't hesitate. Okay, so my talk is on natural language processing, and I'm going to start with a very non-conventional definition of natural language processing, and then I'll go to a more conventional one. So natural language processing for me is just using language to do something. So that could be exchanging information, or gathering information from sources, coordinating actions of different agents. It could also be used to convince other people to do something or not do something. And you can also do natural language processing for its own sake, sort of. So if you're reading a good book, for example, and you're enjoying it, well, in a way you could say that you're simply processing the language in the book, but there's nothing more to it. Okay, so humans do language processing most of the time. There are lots of studies on how long people talk during the day, how much they converse with other people. It turns out that it's a significant portion of what we do in our awake time. So two things: your brain is very good at language processing, and also children have this insane ability to learn language very efficiently, even though they have no direct supervision. Like, nobody explicitly teaches them language, and yet they pick it up very quickly. Okay, and so natural language processing is also something that machines can do. So this is a very extreme example. This is a coffee machine, and that coffee machine is telling me something using natural language. It's really just translating its own internal state, but it's expressing it with language. So it could be just a light that goes up on a screen, but here it's actually translated in language. Okay, so this being said, some machines are better at natural language processing than others. So you've, I'm guessing, heard about ChatGPT. And so even though it seems that they can pretty much do anything with language, some small pieces are still missing. Okay, so this is a quiz for you. All right, so here's a question. The trophy doesn't fit in the brown suitcase because it's too big. What is too big? Okay, and ChatGPT gets this right. And now the trophy doesn't fit in the brown suitcase because it's too small. Now, what is too small? Okay, good. I'm relieved to know that my audience is pretty much human. So the ChatGPT actually gets this wrong. It just starts talking about the suitcase, and it gets to the wrong conclusion. So this is just to say that there's more to natural language processing than just the language. There's also a lot of things that go on about background knowledge and these kinds of things. Okay, so first I'd like to start off by saying what is hard about language in general. So if humans are so good at it, why is it difficult for machines? Okay, so the first, I'm just going to talk about different types of ambiguity. So the first one is phonetic ambiguity. So here are a couple of examples. So if you're an English speaker, you'll notice that when you say, you probably not notice that when you say pin and spin, those are two different P sounds. So the way to notice this is put your hand in front of your mouth and say pin and spin. So pin and spin. And one of them, the first one usually, has a lot more air coming out than the other one. So you might perceive this as the same sound, but they're actually technically two different sounds. I have a really good example in French. So if you say this, this bigram here, if you say canard jaune, the R here is a R, and if you say canard flottant, the R here is a H. So if you're a native French speaker, say it carefully, you'll realize there are two different sounds. You probably never heard that. I certainly never heard that before I was told. And those two sounds in French are identical, at least in perception. But in other languages like German, they can be a sound that actually makes a difference between two words. So here are two words in German, Bure, Buche, and they mean different things. But if you say them quickly, they might sound the same to a native French speaker. So I don't really have other examples, but if you go to Wikipedia and look up allophones, you'll probably have examples in all kinds of languages. Another thing that's really hard about the phonetics of language is that when you're hearing somebody speak, you might hear you're hearing a sequence of words, but really, if you look at the raw acoustic signal, there are no spaces between the words. So your brain is placing those spaces post hoc. So that's also something that children have to learn. Right, so that's phonetic ambiguity. There's also lexical ambiguity. So in a phrase like close to the sun, it's actually not clear what the word close means. So you could be looking at a picture, with a bunch of things on it, and you could say, oh, that thing that's close to the sun. But you're saying it's close in terms of a couple of millimeters on the picture. Or you could look at the sky and say, oh, that thing that's close to the sun. And so that would also be something that is actually very near to you, but close to the sun due to the perspective. Could also mean something close within the solar system, in which case the word close means just a few billion kilometers. Okay. So I like this quote very much by Groucho Marx. In this country, a woman gives birth every 15 minutes. Our job is to find that woman and stop her. Okay, so some of you laughed. That's a good sign. Here, there's a form of lexical ambiguity, semantic ambiguity, which comes from, so technically it's a quantifier scoping issue. But so, in this case, it's a joke, but sometimes there's actual ambiguity and people misunderstand these things. Okay, final example of ambiguity is syntactic ambiguity. So here, she was watching the man with the telescope. So there are two ways you could understand this sentence. Either someone is watching a man and is using a telescope to watch the man, or somebody is watching someone that happens to be next to a telescope, or that's holding a telescope. Okay. And that's something you'll be able to explain by the end of this morning. It's just a different way of parsing this sentence. Right. And so the science of studying these phenomena is called linguistics. Okay. So all of these ambiguities correspond to various levels of processing language. So there's the phonetic level. So interestingly enough, we can sort of separate out each of these levels. So for example, if you're looking at this sequence of characters here, it doesn't really make any sense in English. It's hard to pronounce. You're pretty sure it's not a word in English, intuitively. This here, it kind of looks like a real English word. So if you're not a native speaker, you might think, okay, I've never seen this word, but this looks like something that could be an English word. And in fact, there's a good example of this. There's this poem by Lewis Carroll, which contains lots of these completely nonsensical words, but which is still pronounceable and can still be read. It's a very famous poem, actually. Very famous actors read this poem like it actually means something. Another level is morphology. So certain things can't exist, like cool, it's not a word in English, even though morphologically, why not? And then other words like warmth are valid for some reason. Syntax is another one of these levels. So some sequences of words make no sense or are not acceptable. Other sequences are acceptable. In semantics, even things that are syntactically valid, so grammatically it's fine, but it doesn't make any sense. And then the sort of last level on top of this is relevance. So what you say matters as well. If you say something like, 2 years ago, I lost 20 cents in the street, nobody really cares. If you say something like, I lost my wallet in the metro yesterday, for example, that's much more interesting. Okay. So there are different levels here that you can separate from one another. And they all correspond to different cognitive abilities in general. Okay. So another mystery about language is how children acquire it. So all of these different levels that I've mentioned, children are able to pick up in more or less in sequence or jointly. So here's sort of a chart of what we know about this. So for example, one thing that I mentioned, allophones, we know that children lose this contrast between sounds that are, they lose the ability to recognize irrelevant contrasts. So for example, French children around 12 months in age, they can't hear the difference between canard jaune and canard flottant. Or at least not if they don't pay attention to it. We also know that they are able to pick up words at around month 6 and so on. So we sort of know what children learn and when they learn it, but we still are not sure precisely how they're able to pick it up. And just to give you, so of course, a possibility would be, oh, it's just statistics. They hear a lot of language, they're young kids, they have nothing else to do, so they end up learning this. But the reality is that if you sort of average the number of words that children learn per day, it's about 3 to 10 new words between age 0 and 14. That's actually massive. So one possible hypothesis is that they pick up some kind of structure and some kinds of rules by listening to language, but still not clear how this is done. Okay. So all of these things that I touched on, if you want to learn more about linguistics in general and language acquisition, this is an excellent book. the language instinct, it might actually encourage you to get into research in linguistics. Okay, so one last thing that's really fun about language, and then we'll do things that are not as fun, are garden path sentences. Okay, so we're going to read a sentence word by word. So I'm going to go slowly through this. Okay, so was this somehow surprising to you? So can somebody tell me what the, or okay, I'll give you another example that's even more startling. So this sentence actually took me a couple of minutes to even understand. So can somebody tell me what is complicated about, or what is surprising about this? Yes, exactly. So it's an ambiguity about where the subject is. And so if you only start looking at the sentence, at the first words of the sentence, you actually think that people is the subject when in reality it's fat. So it's, yeah, it's a surprising effect. I have two other examples. This one's in French. And I have one in German that's extremely subtle but is really fun. So if there are any German speakers, okay, so if you don't get it, you can ask me afterwards. This is actually a garden path word. Okay, and that's something, so this processing is something you might be able to explain by the end of the morning. Okay, so now let's move on to the computer part to the engineering part of NLP. So is it possible for computers to deal with all this variety of language? I'm going to sort of give you the bottom line of the talk before the end. So, of course, this is kind of a philosophical question, so this is mostly my take on it. So I would say, yes, computers can deal with language, but there's an if. If the task is well defined, so is it clear how the program is supposed to react to its input? That's not always well defined. Or sometimes people use a program for a purpose that it wasn't made for. It's also possible if the linguistic phenomena are abundantly described. So what are we trying to do? What are the kind of ambiguity that we're dealing with? How variable is the language, and in what way is it variable? So for example, in speech recognition, we need to know what language we're recognizing, what type of speech. So is it somebody reading a book? Is it people talking? Is there any kind of context we need to take into account? And then what is the collection of phonemes in the language? So that's sort of, the phonemes are sort of the variable part in the language. And that is actually true for statistical and symbolic methods. I think you might have heard about the difference between the two earlier. It's just the way that you describe it is a bit different. So describing the variability here for symbolic methods would be done with rules, and for statistical methods, you describe that variability with data. You have to have data that represents the entire scope of variability. Okay. All right. So now to a more conventional definition of natural language processing. So really, it's about it's the science or the engineering part, the engineering science about getting computers to solve some kind of task that involves natural language. Okay. So here are just a couple of examples. So maybe it's answering queries that were asked in natural language. So I get a question like, what's the capital of the states that New York borders? And then I want to answer that using a SQL query. And so mapping that question to a SQL query is NLP. Extracting information from natural language. So here's a sentence. It's actually one of the sentences in Wikipedia about Johns Hopkins University. And so I might want to map this string here to a structured representation that I can then put into a database. So there's a sort of nuggets of information. And then something like finding documents in a large collection, that is very much NLP, and that's basically what Google is famous for. Okay. So NLP is mostly an engineering endeavor, and it occasionally uses insights from linguistics, but doesn't have to. Okay, so I want to say a couple of things about what NLP is not. So NLP is not linguistics. Linguistics, as I mentioned, is the science of studying language. And here language is viewed as something that happens, like a natural phenomenon. It's what humans do. And so linguistics is about finding the best possible tools that will describe language or that will explain the kind of language that we observe. So for example, in phonology, they're interested in how languages pick which sounds to use, how words are built, what types of sentences are acceptable for a given language and how that's determined, and then how humans use language to actually transmit meaning. Okay, NLP is not psycholinguistics either. Psycholinguistics is really how humans process language, what abilities they use when they're listening to language, reading text, speaking, those things. It's also about how children learn their first language, and possibly also about how language changes over time or how it came about in the course of evolution. NLP is not computational linguistics either. So computational linguistics is sort of a subfield of linguistics where you use computers in order to get insights about language. So the goal is the same goal as linguistics. Right. So in contrast, the goal of NLP really is to just accomplish something using language. Okay. Both of these can involve some form of machine learning. And confusingly enough, they might be published at the same conference, really. Okay, so I mentioned machine learning. NLP is not machine learning either. So it happens that NLP has increasingly used tools from machine learning, but it is definitely it's definitely a separate field. It just happens that new machine learning methods were often tested directly on NLP tasks. So this was we had data sets for NLP. NLP has interesting tasks. So people who would design machine learning methods would test them on these data sets. And then conversely, certain problems in NLP have helped develop new machine learning methods. So for example, the transformer architecture was very much inspired by the needs of machine translation. Okay. So NLP is also, so I've told you what NLP is. And NLP is also getting more and more popular these days. So here, just as a basic metric, the ACL, which is the main organizer for conferences in NLP, was founded back in '62. The earlier conferences had just around 30 papers with a single track. And now these days, it's more like thousands of papers, and there's lots of different tracks and workshops and subfields. It also happens that in the past 20 years or so, over the past decades, let's say, a lot of tech companies have built products around NLP. So these are a couple of examples. So things like personal assistants, things like personal assistants have relied on voice recognition and also on a lot of technology around dialogue. And then things like Google also at their core are about natural language processing. And one thing that's really peculiar about NLP, especially NLP research, is that new research has come out of universities, as is usually the case, but it has also come out of major tech companies. So that's a bit new in terms of research, and it's not always the case. Okay, so but before I sort of launch into a very rapid history of NLP, are there any questions on these things? Don't hesitate to interrupt me, really. Okay, so now I'm going to give a very partial history of NLP. And I'm sort of going to date the beginning of NLP with the Turing test. So for those of you who wouldn't know what the Turing test is, the goal of the Turing test is to put a human in front of a computer, or, well, actually, not necessarily a computer, but to put a human in front of some kind of textual interface. And then that interface enables the human to communicate with either a machine or a person. And the idea is that whoever is on the other side has to convince the human that they're human as well. And so that's a task viewed from the perspective of a computer is an NLP task, because they have to they have to read sequences of characters and produce sequences of characters that will then convince a human that they're also human. Okay. And so ideally that thing would be solved by some kind of chatbot. And one of the first really famous chatbots was Eliza. And so that was based on a very, very simple idea. It was able to take in sentences by humans and then produce some kind of answer. Usually it would just ask questions. And it was done in a very clever way. And it was one of the first chatbots that was sort of, that surprised people. Where people were like, well, this thing is actually making some sense. So its only flaw was that it was not very good at producing relevant content, and so if you had a conversation with this chatbot, it would sort of go in circles. Okay. So a couple of years later, there was a programming language called Prolog that was designed, and that language was really intended for reasoning with language. And the first sort of implementation came with a grammar to parse French. So the idea was that, so this is from the first technical report by Prolog, that you could put in these kinds of paragraphs of text with facts and questions. So here's a translation in English. And then Prolog would read these, turn these into sort of a structured representation for knowledge, and would then be able to derive answers to questions. So that worked reasonably well. This part of Prolog was kind of forgotten. It ended up being used mostly for logic programming and not for NLP. But you can use that thing for NLP. Okay. So fast forward about 30 years. Some people have sort of taken this logic from, or the idea behind the design of Prolog, and sort of driven it to its extreme. So Boeing had an NLP system internally that sort of took all these ideas from Prolog, and that thing was meant to solve complex problems that were stated in natural language. So I just have an example here. So even though this was published in 2008, this was like a massive research project within Boeing. So you could take things like this. So an object is thrown with a horizontal speed of 20 meters per second from a cliff that's 125 meters high. So internally, it would represent the sentence with these kinds of statements. The object falls for the height of the cliff. And now what's the duration of the fall? And so this is, this is a question that's a little bit like the suitcase question. You need a lot of context to understand this and to answer the question. So you need a lot of knowledge about physics. And so these kinds of problems will combine knowledge about multiple things, about language and about physics, for example. How did they get this knowledge? Well, they're really, at that time, the canonical way was just to ask humans to write these things down. So you'd put a physicist in front of a computer and say, okay, now go write all the knowledge I need in order to solve these kinds of problems. And there's been lots of research that went into how to do this. Like how can I best get all of the relevant knowledge out of a scientist? They've also done this for biology, for example. And the main sort of takeaway from this research was that human experts really are not reliable, mostly because they are not aware of all the knowledge that they have and all the knowledge that's actually needed to solve these kinds of problems. So that was sort of a negative conclusion, but it also sparked research into a different direction, and that led directly to IBM Watson. So if we can't get humans to write down all the relevant stuff, then maybe we should extract the knowledge directly from text that happens to be around anyway. So maybe confronting humans with the problem of writing down knowledge just doesn't work, but they might actually leave traces of knowledge as they're doing other stuff. So IBM Watson really was just a language processing thing that sat on top of Wikipedia and DBpedia, and that just mined Wikipedia and DBpedia for knowledge, put that into a structured representation, and then use that to answer questions. So it's sort of the same idea as for this Boeing thing, except that the knowledge comes from an entirely different source. So just to compare this to Boeing, this was also, so this is the typical pipeline of IBM Watson. So it has lots of different modules. And here I'm highlighting in red all the things that most likely are statistical modules. So this was, so there's still some symbolic processing to this, but there's also a lot of statistics going on. So this was sort of the beginning of a shift towards more statistical methods. But I just want to emphasize that the shift was initiated earlier. Okay. So now we're jumping back in time to when Google was invented. So before Google came around, typically search engines would just index a bunch of keywords in text, and then they would just retrieve documents based on index. So based on keywords. So you type in your keywords, and you get all the documents that contain those keywords. And if you were a bit clever about it, you could say, okay, either this keyword and this other keyword, or this third keyword, something like this. You could do elaborate things, but it was all based on keywords. And then Larry Page and Sergey Brin came up with something that's even better, especially for the web. And that actually came out directly out of NLP research that was being done at Stanford at the time. So they were in the middle of their PhD and said, hey, we have this new method. This might work better than what we had previously. Okay. And the key to this is that this relied on statistics. So it relied on counting things and estimating probabilities. And that was an idea that happened to work much better for the web. And so that was the main thing here is that these statistical methods, they rely on some amount of data. And so at that point, the internet was large enough to provide enough data for these things to start working well. Okay. Okay. And now I'm really fast forwarding a lot, so 30 years forward. We now have things like generative pre-trained transformers. I think you've had a lecture on these in detail, so I'm assuming you mostly know about this. The way I see these is that I'm going to take an analogy. So Newton's equations can explain the motions of planets. And Newton's equations have a bunch of parameters. So gravitational constant, the mass of the sun, these kinds of things. And so with these equations and those parameters, we can explain what we observe, which is the position of stars, for example, in the sky. And so I see these GPT models as a set of equations with a lot of parameters, way more parameters than Newton's equations. And we use these to explain the text that we see on the internet. So really I see this as an explanatory model of language. What's surprising about them is that they can be actually used to solve NLP models. And what's even more surprising is that they have emergent abilities. So I'm not sure if you have heard of this term, emergent abilities, but just to summarize it, it's essentially, so this is a figure taken from a paper. Here is sort of the size of the model or the amount of data that it has seen. And then this is its ability on some task. And we observe this sort of, this angle here, or how would you say this? Anyway, here the curve is flat, and then at some point it starts picking up massively, right? So more or less, and at different points for different tasks. And so this shift in behavior here is called an emergent ability. What's really interesting also is that there are tasks where the emergent ability goes the other way. So small models are pretty good at it, and then boom, performance tanks and almost goes to zero for larger models. There's a whole prize built around finding tasks where this emergent ability is reversed. Okay, so this history I gave of NLP really sort of looked at tools and at tasks from the perspective of either symbolic methods or statistical methods. So here they're roughly placed on a scale from more or less symbolic to more or less statistical. So obviously that's only one way of looking at this. You could look at it from other perspectives. That gradual shift from symbolic to statistical, that was enabled by the ability of having more compute and more data. So IBM Watson could have been an entirely statistical model, but the thing is, at that point, they didn't really have enough compute to run these things, and they didn't have enough data to begin with, and in order to get to a solution that was decent enough to win at Jeopardy. Okay. And I also want to say that systems on different points of this scale can exist at the same time, and that's perfectly fine. There's no, it's not like statistical methods will systematically be better than symbolic ones. It really depends on the problem. Okay, any questions? Yeah.
I was just making notes, so if you could go 2 slides back. Yeah, this one. On the x-axis, there's the number of parameters, or what was on the x-axis? On the graph.
This here.
Uh-huh.
So, honestly, look at the paper and look at the specific figure I copied. I'm thinking it's number of parameters.
All right.
Yeah. But there's also so that's actually a really good point, because there's a bit of a confusion there. Usually larger models will be trained on more data. So it's not entirely clear. So on the x-axis is probably the rough number of parameters of the model, but really if you trained a large model on less data, it's not clear whether or not it would actually have the emergent property. So they're slightly confusing two things which are correlated. Yeah.
I think like there is like the chinchilla like rules, which they say that actually the number of floating operations is what matters. So if you have like a smaller number of parameters and you train longer, it may come similar if you have large models and you don't train that long. So.
Yeah, and all of this is ongoing research. Like we don't understand all of it, but yeah, these are good points. Yeah. Okay. Okay, so right. So I just wanted to say a few things about symbolic versus statistical NLP. Really, this is just because I'm guessing that you're getting bombarded with how statistical NLP is much better than symbolic NLP. So I thought it'd be good to remind people that both are possible, and usually any given system is sort of in between them. So advantages of symbolic NLP usually, generally, not always, are more interpretable than statistical models. So you can usually figure out how some system came to a conclusion. They are, so this is a bit paradoxical, but they're usually better at generalization in certain ways. So for example, if you have a very rule-based model of English language, it's very easy to learn a new verb because you can just give its base form and then you have rules for conjugation that'll come out immediately. It's also very easy to acquire new words because you can place it exactly in your semantic network in relation with other words around it. It's also usually easy to incorporate domain-specific knowledge. So for example, the Boeing example I showed you, the whole point of this is that you have your module that processes language, and if you want to add knowledge about a certain part of physics, that's very simple to do. You just add rules to the physics module, and that thing is already working very well together with the language processing module. Actually, one of the purpose of this Boeing thing was that they have to produce manuals, users manuals, and especially manuals for people who repair planes, for example. And these manuals had to be translated in multiple languages. And so in order to be sure that they made no mistake, all of these translations actually relied on a common sort of knowledge base about physics or about Boeing engines. So they can be things that are actually mission critical. Right. So in contrast to that, advantages of statistical NLP. So really, historically, we've seen that a lot of the progress made over the last decades or so happens to have come from statistical models. So that's sort of the way it's happened. In fact, there's a really famous quote by Fred Jelinek, who gave his name to the JSALT workshops. So he is reported to have said, so this is kind of debate, the exact quote is somewhat debated, but the idea is that anytime a linguist leaves the group, the recognition rate goes up. So the idea was that every time he replaced, so he had linguists and engineers working on speech recognition, but whenever a linguist was replaced by an engineer, usually the rate went up. So the idea here was that linguistic intuitions about language might not have been the most useful tool to build a good speech recognizer. Okay. A very abstract argument is that we have a lot of observations about language, and so it's a bit more obvious to simply model whatever we see rather than build elaborate theories and then test them. So instead of trying to guess what the right model of language is, you can simply let the data speak for itself and sort of build whatever model will fit your observations. So this has a lot of, I mean, we could talk about this for hours. In terms of machine learning, it's not necessarily obvious why this is right or wrong. You don't need to design any features in statistical NLP, so we'll see this in a minute with log linear models, but that's a big advantage. And I want to conclude this comparison with the fact that so statistical NLP is more on the side of observations, symbolic NLP more on the side of theory and rules. But really, it's absolutely possible that while these two are somewhat separate, at some point we might converge on some kind of unifying theory that explains phenomena in language, and that also happens to be useful for NLP. So the analogy I really like to use is, so you might know that Tycho Brahe was an astronomer who made a lot of observations, just noted down the position of planets over his entire life. And then his student Kepler looked at all of these observations and turned them into a set of 3 rules. There were sort of 3 laws, really, which were called Kepler's laws. And then Isaac Newton came around, and he had his theory of mechanics. And with his theory of mechanics was able to derive Kepler's rules. And so here the idea is that we went from lots of observations that made absolutely no sense to some interpretation of those observations. We didn't really know why these laws were true, but they just happened to be observable in the data, and they happened to explain some of it. And then finally we had a theory that would explain all of these observations and even make predictions beyond that. So if you use Newton's rule to derive the third law of Kepler's third law, it actually gives you a formula to compute the mass of the sun. That was something that was entirely novel, but one of the constants involves the mass of the sun. So that's something that they could predict. Okay. So now I'm going to shift to a slightly different topic. So if there's any other questions about NLP in general, now is a good time. Later is also a good time.
To the last point that you had on the slide, do you see any of that actually emerging at the moment? Like, we have large language models based on NLP, and do we see any progress in deriving any rules that would be emerging from that?
That's an excellent question. Definitely not. I mean, I'm not seeing any new theories that would explain this. I think one really hard problem that's related to this is that people in optimization, so theoretical machine learning, are trying to figure out why generalization even works. Like, how is it that you can train a model on a certain amount of data and then it generalizes well to the other parts? That's something that is not entirely clear. If you go to a conference like that, you'll see that they all have lots of interesting theorems, they all make very different assumptions, and they can prove lots of things, but those assumptions generally don't hold in practice. So we're still not entirely sure how to deal with this. But I really believe that at some point somebody's going to come up with a unifying theory that explains pretty much all these phenomena that we observe empirically.
Because I've heard about that this is the time when linguists should be happy, because all of the machine learning engineers are doing the hard statistical work and they just gather the results. For instance, the discussion was about machine translation, that there might be some abstract way how to represent the language because it's easy to translate in the statistical model. So there has to be a representation which is unified for basically every language.
So there's a lot of things I could say about that. That's the idea of having some kind of interlingua or a logical representation or semantic representation for language. This works to some extent, but it's mostly, I mean, this is a hotly debated topic. I think people like Fodor have discussed this. It's not entirely clear whether humans have but this is more of a philosophical kind of topic. We can talk about this later. But yeah, the idea that humans have some kind of unified meaning representation, it's not clear whether that's the case.
Okay, thank you.
Okay, and I'm super happy to talk about this offline as well. All right, so now we have 40 minutes for log linear models and for probabilities. Okay, so I'm going to now focus so this was sort of a high-level overview of NLP. And I'm going to focus really on one specific aspect of it, and that's how you can use probabilities in order to model phenomena in language, and then use that to solve NLP problems. Okay, so things like GPT-4 rely a lot on this modeling paradigm, and that happens to be the dominant modeling paradigm in NLP. It's also used a lot in other areas, like in speech, for example. So I'm going to look at 4 things: probabilities, log linear models, how to estimate parameters of log linear models, and then have a very short blip on gradient descent. So if I had to place this on the spectrum, I would say that log linear models are roughly here. They still have a lot of symbolic structure, but really they're a major breakthrough in terms of in terms of statistical models. Great. So the first thing is, what is a probability? I want to hear opinions. Nobody, you don't know what a probability is? Do you have some kind of intuition? Yes. Take the mic.
It's a function from a space of events to 0, 1. The whole space should map to 1. And you have that third rule about if the intersection is 0, then it should sum.
Okay, yes, that's an excellent definition. So that's sort of the theoretical definition of probabilities. Does anyone have a real world kind of definition of probabilities? Like when you say, oh, I'll probably go to the movies tomorrow. What do you mean by probably? Yeah, take the mic.
Like the likeliness something will happen.
Okay, so sort of degree of belief that something will happen, some kind of measure of, yep, okay. Does anyone else have another definition? Yeah.
I think you're touching a really difficult one here, because the only clear definition that I've ever heard was that if I measure something repeatedly, I will get the results that resemble the distribution of a probability. But that's the only thing that I've ever actually believed, because all the others are philosophically extremely difficult.
Okay, so I'm super happy you all made these points, because those are exactly the definitions I had. So the first one is, yeah, if I repeat the same thing lots of times, what'll come out? Do I believe that something is true or not? Like, can I give some kind of measure of that? So, and then the last one is theoretical, and I'll get to it. So really, those two were just examples to sort of get you thinking about this. So if I'm tossing a coin, what's the probability it lands on tails? You all have some kind of intuition of what that means or how to answer that. Same with dice. But you can also use probabilities to answer much more complicated questions. Like, I'm playing poker with someone and my opponent gets a royal flush 3 rounds in a row. Royal flush is the best possible hand. It's extremely rare. So if somebody gets it 3 times in a row, are they cheating? I mean, they could just be extremely lucky, but really, I mean, this is kind of unbelievable, right? At least I'd be very mad that I lost 3 times in a row to this kind of thing. And so that's something that probabilities can be used for. They can quantify this belief whether or not somebody's cheating. Okay. So for that, to answer that question, typically you need some kind of machinery, some kind of mathematical tooling. And so that thing is called, the main tool is called random variables. Okay. So I'm just going to go with a definition and a bunch of examples. It's okay if you don't, if not all the definitions stick. It's fine. The main thing that I want to get across is how we use these things for NLP. So a random variable is a function that maps the outcome of an experiment to a value. So for example, my experiment is I take a coin, I flip it, and then that's it. So it lands on one of its sides. And then I can define something that's a random variable that I call x. And if the coin lands on heads, then x will be equal to 1. And if the coin lands on tails, then x will be equal to 0. Okay. So the randomness here is that I'm flipping a coin, and then that x value is determined by whatever comes out of it. So other examples are, for example, in the poker game. So I could have a random variable that says whether or not my opponent cheated. So we play a round of poker. My opponent cheats, then y is equal to 1. Or we play a round of poker, and my opponent doesn't cheat, then y is equal to 0. And I can also have a variable that will tell me whether or not my opponent was dealt a royal flush. So it's just an indicator thing. We play a round of poker. That's random to some extent. And then the random variable here takes some kind of value based on the outcome. Okay. And the whole point of having this is that we can reason about the probability of the values we can reason about the probabilities of these kinds of events using random variables. So how likely is it that x is equal to 1 is the same as saying how likely is it that the coin lands on heads. And we write that down, p of x is equal to 1. So very loosely, this quantity here is supposed to represent the proportion of outcomes that would result in x. So if I flip lots of coins, what's the proportion of events that will result in the coin landing on heads? Okay. So terminology. Random variables are not random. They're not variables either. In fact, they're functions because they map from some kind of outcome to a value. They're also deterministic, so definitely not random. The only source of randomness really is the outcome or the experiment. Okay. All right. So an example from NLP, like why do we even need this in NLP? So let's say our outcome space are the emails that I receive, and I'm going to. So the experiment is I receive an email. That's it. And then I have a random variable called x that's equal to 1 if that email is spam, and 0 otherwise. So it might look like this. This is the actual email I receive. So the first two are spam. The third one isn't. So this is my experiment. This thing comes out, and then I can compute the value for this random variable. And so the idea is that now I'm getting a new email. So I'm running another experiment, and I want to know the value of x. It so happens that I have no clue whether or not this is spam, so I can't determine the value of that random variable. Right? But we might be able to compute how likely it is that x is equal to 1 and how likely it is that x is equal to 0. So even though I can't determine the actual value of x, I can get something that's still informative. Okay, so why is this better than just applying a bunch of rules that will tell me yes or no, this is spam? So the observations that I have of spam might be contradictory. It's not always obvious whether an email is spam or not. And also, if I have data, for example, then the x values assigned to it might be noisy. So maybe somebody labeled an email but was wrong, in fact, and turned out to be not spam, even though it was. Okay. It's also interesting, so for spam might not be as interesting, but in other domains it's interesting to have a more nuanced sort of grading of these things. So it might be more interesting to know how likely something is spam rather than knowing whether or not it's spam. Maybe in some cases it's actually borderline. Okay. And then this is more technical argument. Probabilities can combine nicely with multiple sources of information. We'll see that in a bit. But I can have more than one source of knowledge and combine it. Okay. I hope this isn't too confusing. All right. Anyway, you can ask questions. Okay, so a more typical task of NLP would be that my outcome space here are strings of characters. So I just get, my experiment is to draw a string of character from somewhere. So for example, I draw a piece of text from the web, or something like that. And then my random variable is still called x, and it's equal to 1 if the sentence is sort of proper English or acceptable English, and 0 otherwise. So here are a bunch of examples, Borislav lab programs. Most English speakers would not accept this sentence. Borislav programs in the lab, probably people would accept it. Frederica programs in the lab with Borislav, that's fine. And Borislav, most people would not accept this. So that task you might recognize as language modeling. And we can also, we can do this task with probabilities. We can also do it entirely without probabilities, and we'll see something like that in the lab session. And then I think in the second lecture you'll also see how we do this task with probabilities, how we use it to model this kind of phenomenon. Okay, so now on to some useful properties of probabilities that we sort of need to know about in order to use them. So I think at this point I've hopefully motivated why we're going to use probabilities for language. We don't strictly have to, but it's usually a good idea. This is the main takeaway. Okay, so probabilities are always positive. So the likelihood that x is equal to small x is always positive. If I sum over all the values that capital X can take, then that's equal to 1. And then I have this additivity property that the probability of two disjoint events here, so A and B are two disjoint sets of values that X can take, then the probability of that union is just the sum of the probabilities. So these are actually super important axioms, but we don't really need to keep them in mind, except for, we'll see. You'll see that they will apply later on. Okay. So a few other properties that are useful. We might want to reason about the fact that we have different random variables, and they each can take different values, but some combinations of values are more common or more likely than others. So for example, if we have two variables, x is a question and y is an answer. So imagine that my experiment is I draw a question and an answer. And then x is the string value of that question and y is the string that represents the answer. Then some combinations are more likely. So for example, usually the correct answer is more likely. And so you can see this visually as, for example, this map here. So imagine that you have here a bunch of questions along, a bunch of questions along the x-axis here, and a bunch of answers along the y-axis. Then larger squares here indicate that it's more likely to have this combination than to have this combination, for example. Okay, so we'll note this as probability of x is equal to x, comma, y is equal to y. Really, it just means the conjunction of two events. One is that x is equal to x, and the other is that y is equal to y. We can use this to do something called marginalization, so we can re-express the probability here that x is equal to x as the sum of joint probabilities. So this is sort of the probability, well, yeah, that's what it is. We'll use this at some point. Another thing that's interesting is conditional probability. So sometimes some of the variables will be observed. So we'll actually, for example, if, again, with our example that y is the answer to a question and x is a question, we might actually observe the question. So we'll be given the question, and now we want to estimate the probability that the answer is equal to y. And so for that, we'll use something called conditional probabilities, which are defined like this. So the definition's might be a bit cryptic. One way to understand this is that we had this distribution, this joint distribution over y and x here. So here, if it's lighter, it means it's a more likely combination. If it's dark, it's a less likely combination. And we're just going to set a value for y here. And then we're going to look at, along this line here, what the distribution for y is. So we'll get different distributions here if we pick different values for y. Okay? So if the question is different, then the distribution over the answers is also different. That's the idea. Okay? So last useful thing is Bayes' rule. It's relatively simple to prove from the properties I just mentioned. It's just a combination of two things. And this is actually a very important theorem. It's used a lot. And I'm going to give you a very concrete example. So there were a bunch of essays that were written in the early years of the United States that were gathered in a thing called in a corpus called the Federalist Papers. They were just papers in political theory, and they were written by three people, so Hamilton, Jay, and Madison. But the thing is that they didn't, at that point in time, it was not advantageous for them to be famous for these papers, and so they did not sign them. So these papers remained anonymous, and it's a collection of maybe slightly less, between 50 and 100 essays, I think. So it was clear to people at the time that these were the three authors of the papers, but they didn't know for each paper who wrote that specific paper, right? So for each paper, there are three possible authors, essentially. And how would you identify which author wrote which paper? So who wrote each of these essays? Well, it turns out that you can solve this, you can answer this question by using Bayes' rule. So probabilities together with Bayes' rule. So the way I just want to go through the formal framework of doing that because I think it's really informative. So our experiment here is that we pick an essay at random from the Federalist Papers. We have two random variables, A, which designates who the author is of the essay, and then X, which contains the text of the essay. So that's a pretty straightforward experiment. Just pick a page from that book, and then we have two variables. One is observed, so we can observe the text of the essay, but we don't observe the author. We don't know who that is. But we can reason about how likely it is. So for example, we want to know what the probability is that the author is Hamilton, given the text. Okay. And the thing is that we can estimate this other probability, the probability that the text is equal to X, given that the author is Hamilton. So the way to do that is you just pick at random something that Hamilton wrote, so you know that Hamilton wrote it, and now you try to reason about the probability that this text came about. So you sort of flip the experiment around. Okay? And then you just apply Bayes' rule as is. So on the left side here is the quantity that you want to compute, and here on the right side you have this other quantity that you're able to estimate. Okay? Then you also have to specify what this prior is here, but all of this can be done. So just a few words that you might hear later on. So this thing on the left here that we're interested in is called the posterior probability. This part here, which is also in blue here, is the likelihood. And then this last thing that we have to add is called a prior probability. Okay. And it turns out that this Bayes theorem is actually a central part, and people have written long books about how this was used to determine who wrote which essay. And it turns out that it works great. You can with high confidence determine who wrote each of the individual essays. Okay, so last thing of interest in terms of probabilities is expectation. So if x is some random variable that takes real values, so for example, something that'll tell me the number of words in an email that I picked at random, or whether an email contains a certain word, that thing has real values. And I can compute a quantity called the expectation. It's also called the average. You can think of it as the average. Has lots of interesting properties. It's linear, and then the expectation of the sum of variables is the sum of the expectations of the variables. Okay. So how do we use this framework in practice? So usually we'll express the type of stuff we're interested in as random variables. So for example, for spam classification, we've gone through a couple of times. The experiment is that I get an email. I have two random variables that I'm interested in. One is the text of the email I receive. So this random variable here maps an email to its string representation. It's just the content. And then y is I'm going to define as 1 if the email is spam, 0 otherwise. Okay. And now I can ask different questions. So p of y given x is, given that I received this email x, is that email spam? I can look at p of y, so how likely is it that an email that I receive is spam, independent of its content. I can look at p of x, how likely it is that I should receive email x. Why not? And I can also look at p of x given y, so how likely is it that I should receive the email with text string, well, with content x, and then making an assumption about whether or not it's spam. So this one's a bit less intuitive, this third one. And in practice, we're really interested in this first one. That's usually the one we're most interested in, but not always. And now I'm going to go into more detail about how we compute this thing. Because for now, I've only mentioned sort of in theory that these are interesting quantities, but I didn't say how we were going to compute them. And so the answer to that question is log linear modeling. So we can use log linear modeling for a bunch of tasks. So spam classification, also sentiment analysis. So here the input is similar. It's a piece of text, maybe together with some metadata. And the answer is a label. Doesn't have to be a number, it can be anything else. You can also use this framework, log linear modeling, for an entirely different setting that's not necessarily NLP. So if you know about BirdNet, for example, you could, in theory, do something that looks a lot like BirdNet, where the input isn't text, but rather some kind of spectrogram or some kind of acoustic signal. And then the output is a label that designates a certain type of bird. Okay. So our goal is to compute p of y given x, say the likelihood that an email is spam or not spam. And we have a bunch of examples of emails that are spam and emails that are not spam. So we still have our two random variables, x and y, and we have observations, simultaneous observations of x and y. And now we want to be able to estimate p of y given x. Okay? So one way to do this is just to count observations. So we could define our probability of p of y given x as how often do x and y co-occur, and then we're going to divide to normalize it by the number of times that x occurs. Okay. That's a possible approach, a possible definition. Does anyone see a problem with this definition? Like, what if you use this in practice? What if you use this for your own email? So x here is an email. Y is whether or not it's spam. So especially I'm interested in this here. So if you counted the... Yes, exactly. So if you started counting the number of distinct emails you receive, it would probably be equal to the number of emails you have received. I've never received, well, okay, I might have received the same email twice, but really usually this is a mistake or something that was not intended. So the problem is that pretty much every x is unique, and so we'll have to store lots of counts. So we might as well store this table entirely, and we might actually consistently predict 0, because if I'm getting a new email, then its count here and here will always be 0. So I won't be able to even define this probability for something new that I receive. Okay. So instead, it's a better idea to use some kind of compatibility score. So I'm going to define probability of y given x as some kind of measure that tells me whether that email is compatible with being spam or being not spam. Okay. So the way we're going to design this score is that it needs to pay attention to those things, to the properties or the characteristics of x that are relevant to predict y. Okay, so this is a bit hand wavy, it'll be clearer in a minute. But really, we want the score here to pay attention to whatever in X is relevant, whatever feature in X is relevant to predict Y, or at least to be correlated with Y. Okay? So for example, this score needs to be higher if certain words are capitalized and it's a spam email. So lots of words in spam emails tend to be capitalized. It needs to tell me whether or not the email contains lots of exclamation marks. So presumably if there's lots of exclamation marks, it's more likely to be spam. But if the email contains my first name at the beginning, it's less likely to be spam. So all of these sort of properties of X need to be taken into account by score. Okay. And then this score also needs to verify the axioms of probability. So I'm going to define the probability as the exponential of the score. So that way it's always going to be positive. And I'm going to add this term here. Oh, I got the definition wrong. I'm going to add this term that's supposed to normalize it. So here I'm missing something, which is, here on the left there should be a sum over X. Yeah, I forgot that. But it's on the other slides. Okay. So the score here I'm going to further define. So how am I going to compute the score? It's going to be a sum of a bunch of things. Okay, so it's going to be I'm going to introduce a set of functions called features that take as arguments the input text and then the possible label. So that thing is going to have some kind of real value. And each of these functions is going to get its own weight. I'm going to multiply both together to get some kind of quantity, and then I'm summing over this quantity. So really, this is just a general definition. This isn't the consequence of anything. I'm deciding that the score is going to look like this. Okay? So the important part here is that I introduced something called a feature. So just a few examples of what a feature would look like. So a feature is a function. It takes as input, in this case, some kind of email and then a label. Label can be spam or not spam. So I'm going to define this first function as, so if y is equal to spam, then that function will be equal to 1 if there's a word in X that's capitalized, otherwise 0. If it's not spam, that function is always equal to 0. Other example of features are, it could map an email to the number of exclamation marks it contains. It can have the converse for an email that's not spam, for example. So this is useful because most spam emails contain exclamation marks. So this will be a good indicator. If this is non-zero, it'll be a good indicator that some email is spam. But maybe some emails that are not spam also contain exclamation marks. So I kind of need to take both into account. So this is what this other one is supposed to do. Okay, and then I can also have a different feature function that's about whether or not my first name appears in the email. So really here I'm absolutely free to design any kind of function that maps from the space of inputs and outputs to some kind of real value. How to design this thing is entirely up to whoever is building the system. It's an art in and of itself. There's a lot of research that's gone into this. Okay, so to summarize, really what this thing does is it maps a string. Okay, I'm missing one of the arguments. It maps a string and a label to a vector here. So these things will have values that are usually real numbers. So f maps a document and a label to some kind of real valued vectors. Okay, and so what I get is this here. So this is just a simplified form of what I wrote before. So here, this is the sum of the theta i fi of xy. I left out the sum because I'm writing this as a in vector form. So this is just linear algebra. Okay, so in this equation here, we have the feature function f. So f maps a set of strings and a set of labels to a vector, a real valued vector in high dimension. That's usually what happens. In some cases, it isn't, but for our purposes, this is what's happening. This f of xy is called the feature vector. And then theta here are called the parameters of the log linear model. So theta is some kind of real valued vector. And then this z here is a normalization factor. This is to ensure that this is actually a probability that where things sum to 1. It's just to make sure it's an actual, has the properties of probability measures. Okay, so we've mostly been doing a bunch of rewriting at this point, defining models, defining a model of probabilities. The only thing that's new is that we've introduced this feature function and then this set of parameters. So all of these things have to actually take values, so you need to define f somehow. It's not something that exists, it's something that you need to, whose content you need to design. And then you also need to set those parameters theta. Okay. So how do we set the parameters? Well, this depends on our choice of feature function. I'm going to make an assumption here to sort of simplify the discussion, which is that we're going to assume that this function f contains all the relevant information to the problem. And by that I mean that if we could set the parameters properly, then we would perfectly solve this classification problem. So this probability here would reflect reality if we were able to solve theta correctly. So in practice, that's not always the case. In practice, f might be somewhat insufficient. Maybe it ignores certain features of x that would be relevant. It all depends. But usually you try to make this feature function as exhaustive as possible so that it contains all the information you need. Okay. So I said something that was a bit ill-defined, which is I said we'd be able to solve the classification problem. But really, what does it mean to solve the classification problem? Like, what kind of probability would we want here? Like, what do we want this to be? So the common exception of this is that this should track the observed probability in the data. So we want this p here to represent the distribution that we have that comes out of a set of observations. Okay. Yeah. So presumably, the p that we have parameterized would track the real probabilities. Okay. The thing is, we don't know what the real probability is. So for example, if you have a coin that's unfair, so that's not perfectly balanced, you probably wouldn't know what the likelihood it is that it lands on heads. So let's say you have a coin that lands on heads more than 50% of the time because it's weighted in a certain way, but you don't know exactly how it's weighted. How would you figure out how likely it is that it falls on heads? Yes, that's probably the most straightforward approach, is you would just throw it a bunch of times, see how often it lands on heads, and then just use that as the probability. And that's kind of what we're doing here. So the idea is that we don't know the real probability, but we have a lot of samples that were drawn from the probabilities. So it's like we've run a lot of experiments and we know the outcome. So in my case, I mean, in the spam classification thing, the idea is that I've received tons of emails, tons of spam emails as well. And so those are observations about the distribution of emails versus spam emails. Okay. So what we want really is for this probability that we're parameterizing to explain the samples that we observe. That's the key idea. Okay. So I'm just going to sort of introduce a bit of notation. The samples here, I'm going to write down as pairs of xi and yi. So an email and whether or not it's spam. And I have n of those. Also, I keep talking about spam email, but really this is a very general framework that's applicable to lots of problems. So I'm going through sort of probabilities for machine learning 101 here. I'm just using email and spam email to make it more concrete. Okay, so we can actually talk about the probability of observing the sample. And how we're going to do this. So probability of this sample is the probability of all of the conjunction of all of these observations. And we can re-express that as the product of the probabilities of each event. So don't worry about the math, really. This is just because we are assuming that they were drawn independently, and so we can rewrite it like that. And then we can use the definition of conditional probabilities to rewrite it as this. So on the one side, the product of the label given the input x times the product of the probabilities of the inputs themselves. So each of these things can be rewritten, and then I'm grouping these differently. Okay? I can take the log, because that's really convenient. It turns the product into a sum. So now I have two sums. So our log linear model can say something about this probability. We've used it to define this probability here. And then this probability here doesn't depend on our model's parameters, so we're not really interested in this. So now maximizing the probability of S is like, so a probability of the observed sample is like maximizing this quantity here. So I'm just going to go back briefly. So maximizing P of S is like maximizing the log of P of S. It's like maximizing this sum here. But this part we can't say anything about. So we might as well just maximize this one here. Okay? And then as we're maximizing this, I've actually introduced theta here. So that thing is the set of parameters of the log linear model that we're using to define this. It's not really a random variable, at least not the way we've defined this, but it actually does influence the value of these probabilities. So I sort of added it back in just to make you realize that this P here depends on, sure, it depends on Y and X, but it also depends on theta. So this whole thing here, we can say is a function of our parameters theta. Okay? That's a really important point. Okay. And that thing is called the log likelihood. You might come across this word. So maximizing the log likelihood is like minimizing the negative log likelihood. This is much more frequent than maximizing the log likelihood. So this is just a rewrite. And if you plug in the definition for P here under the log linear model, this is what you get. This is just a rewrite of this. So this is the numerator, and this is the denominator. So our idea here is that the smaller this quantity is, the better our choice of theta. So if we can get this thing as small as possible, ideally 0, then we've probably picked a really good theta. Okay? And so that thing here is called a loss function, because it measures how good our parameters are. Okay? So just a note, sort of more generally, there's lots of ways that you can define a loss function. This negative log likelihood is extremely common for statistical models, especially for NLP. I'm going to skip this. These are just properties that we might want for a loss function. Well, actually, so a loss function, a good loss function, typically we want it to be continuous, so that if we tweak the parameters, we can measure its influence on the loss function. We might want it to be convex. So this is a really helpful thing in analysis. It gives us certain properties about the solutions that we find. We might want it to have a closed form solution for the minimum, so we might want to be able to solve for theta directly. That is very rarely the case. In this case, it really isn't. And then something that we really like is for loss functions to be differentiable. And I'll show you in a minute. Okay. Right, so how do we find the parameters that minimize this quantity, this negative log likelihood? We don't have a closed form solution, and so we're going to resort to something that's used typically in optimization called gradient descent. We'll compute the gradient of this quantity, negative log likelihood, and that'll tell us how to tweak the parameters to get to a better place. Okay. So this is really just the formula of the gradient. If you compute it, this is what comes out. What's interesting in this is that it's actually a sum of two things. So one is the observed feature. So this is feature number k as it occurs in the data. And then this is feature number k as our model predicts we should observe it. So if this is a bit hard to see, but whoops. This is a bit hard to see. But this thing here is an expectation under the probability distribution defined by our log linear model. Okay. I think I have it on another slide. Okay. So this is our update rule. We'll change theta based on the gradient in the following way. And so in that update, there is one part, the features that we observe in the data, one part the expectation. So this thing here that you can see here is the expectation of the value for that feature given that x takes a certain value. So given that the input takes a certain value, what would this feature look like? That's what it is. Okay. So that update rule looks complex, but it can be seen as something that's very intuitive. So our model has a certain, so our model defines a probability. So it has a certain, it also defines a certain expectation over the features that we should be observing. And so what we're doing with this update rule is we're confronting what our model expects with what reality actually looks like. And so you can see that if the expectation here is higher than the true count, then that corresponding weight should be decreased, and so this will also decrease the expectation. To convince yourself properly of this, I think it's better to look at actual examples or to play around with this. And there's a really excellent visual explanation of this. So a professor at Johns Hopkins called Jason Eisner has a really good tutorial on this that he built with, I think, Frank Ferraro. And so it's something with a bunch of sliders where you can play around. It's very visual, and it helps you understand the intuitions behind log linear modeling. It's good to understand these intuitions because they also tell you a lot about gradient descent in general and how other statistical models work. You can find this on Jason's website. Okay. So what happens when we do gradient descent? So for log linear models, gradient descent will actually find the global minimum. And that is because the negative log likelihood is a convex function of the parameters. So that's a really nice property that definitely doesn't exist for deep learning models. But it turns out we have it for log linear models. So what happens when we find the global minimum? Does that mean that when we're at the global minimum, we've perfectly solved the problem and our probability tracks the real probability of the data? So not necessarily. So what happens at the global minimum? Well, all the derivatives go to 0, and so we can write, for each feature, we can write this type of equation. So there at the global minimum, the true counts, here on the left, and the expected counts match up perfectly. But that's all. That's all we can say. It doesn't necessarily mean that our probability perfectly tracks the probability of the data. Can anyone see why? Yes? But to take the mic in.
Because the number of elements don't mean that the elements are correctly placed.
Yes. Yes, but so take the extreme, for example, where I only have a single feature function that doesn't tell me a lot about the email. Like what is the best I could do in terms of prediction if I only had one feature function that, for example, just tells me about whether or not there's a capitalized word in the email? So that feature function will track the distribution of, so our log linear model will track the distribution of that feature function in the data. But that doesn't mean that our prediction is very good. So what happens is that, yes, we are tracking here the true counts and the expected counts, but we can only do as well in terms of predicting whether or not an email is spam. We're limited by the feature functions that we have. So that's what happens. So we get to the limits of the capacity of the model. Okay. All right. And also just to note that this is not a closed form solution, and it's not a perfect solution either. Okay, so this is the end of this part of the lecture. Any questions on log linear modeling? We have a couple of minutes, I think. So I just want to emphasize that this was a real fast forward through log linear models. If you take an NLP course, this will span multiple lectures and multiple lab sessions. So I hope you got a couple of intuitions. I tried to get the main intuitions across for log linear modeling. But if you're confused, I wouldn't be surprised. And if you have questions, don't hesitate.